at some of the links that are here under the instructions. Okay, the first one's sampling distributions. I really would have done this with you earlier, but you know, we got yanked out of school. So the idea of a sampling distribution is this big mound here is the population. And then you're able to take samples of different sizes, 5, 10,000, 100,000. Let me just do a sample of 5. Actually, I wanted it to animate. There we go. So what it's doing is it's pulling out a sample, it's averaging it, and then on the third line down, it's giving you the results. Now, if you do this a bunch of times, you notice the blue one is still a normal curve, but the spread is a lot smaller. In other words, the standard deviation decreased. And in fact, the more samples you take, the smaller it should be. I should clear this and start over. Hold on. So if I go 10,000. So that's what we talk about. The aim gets better when you have a larger sample size. But this only happens in what we call the sampling distribution. Well, it turns out that the formula we use for that is what we're using for confidence intervals. So that's the connection between the two, why we did sampling distributions first. Let me show you this other website here. Actually, there's two on confidence intervals. The first one is for means. And so we're going to draw a sample. Actually, I'm going to do 25 samples. So I just click the sample 25 button. Each of those intervals is what we would call a confidence interval. So it's drawn from a sample, and then using the standard deviation, you notice they're all the same size. That's because the proportion, actually for this one it would be mean. The mean didn't change and the standard deviation didn't change. But the centers are all over the place. And that's because that's just sampling variation. You know, we had that on one of our tests last semester. The hit percentage right now is 100%. You see right down there where my mouse is?
Mm-hmm.
Okay. This was supposed to be, thank you for drawing all over the screen.
Oh my God, I did not know you could see that.
That's fine.
I'm so sorry.
That's okay. This is a 95% confidence interval, but we hit on 100% of them. Well, the way I would explain that is, it's okay to go above and beyond. Like, you know, you do more than's expected. But when we do a bunch of samples, if I just keep clicking the sample 25 button, okay, now I'm going to do like 1,000 samples. So my total is 1,000. Now look at the percent hit. Now what that means, percent hit, is the true mean is that yellow line that runs vertically. And if an interval contains that line, that's considered to be a hit. In other words, the interval did contain the true average. But since we did 1,000 of them, only 95 actually hit. In fact, I wish I could, let me reset it, see if I can show you one that doesn't hit. There. So you see those red ones? That green line is out of the interval. So in other words, and this one's a really bad run of 25 because the percent hit's only 88%, which is, I would say that's less than advertised, right? It's really advertised, oh, you should be getting 95% or better of your confidence intervals that are going to capture that true mean. Now here's the part that you got to really wrap your head around. We usually don't know what the true mean is. So we're just hoping and praying that that interval, that confidence interval, has the true value inside of it. And then let's see, one more is confidence intervals for proportion. Okay, again, I'll do a sample 25. Let me play with the population proportion. So right now it's set at 0.5. Let me scoot it up to 0.7 and redo a sample of 25. You see how they all scooted over toward 0.7? But some of them missed. Like there's one that missed, the one in red, right? But look at my percent hit over here on this left side. I'm at 96% right now, which is pretty good, right? It's better than advertised. Well, what if my confidence level decreased? What would happen to my intervals then? Let me reset so you can really get an appreciation for this. Drop it way down here. I'm less confident, but notice my intervals got smaller. How do you get more confident? You make the intervals bigger. See that? So here's the example I would tell you in class. And I would usually set this up to make everybody feel really nervous. I'd say, you know what, I'm going to guess your weight out loud, right? And I would pick on somebody, usually a female, because they're really self-conscious about their weight. So since Beyonce just laughed, I'm going to pick Beyonce. I'm going to say, Beyonce, I'm going to guess your weight is somewhere between 1 and 1,000 pounds. Am I correct?
Yeah.
All right. So you see, I'm almost 100% confident. Well, BFD, right? Big deal. You made your interval super wide. That's why you're very confident. But if I shrink my interval, if I say, are you between 72.3 and 73.9 pounds? Okay, that's a really tiny interval comparatively speaking. And it's like, even if you're, and that would be like deadly almost for you to be 70 pounds. But even if you were in the 70s, because I've made my interval so small, there's a very low chance that the true value is actually in my interval. So don't always think that higher confidence is better. It's a combination of factors, which includes sample size. It's actually these three sliders that you see here. It's the population proportion, it's the confidence level, and it's the sample size. All three are contributing. And if this looks a little familiar to you, this was the project that we did about the movies. If you think about it, we didn't do confidence levels, but we said, you know, if you start with 1%, what's your chance that you actually get the other percentage? What I was really trying to get at there was that other value could be within a confidence interval. Anyway, this background stuff, if you don't get it right now, maybe it'll dawn on you later on. But I'm hoping that this video comes through really good. If not, you can watch this on your own. I made this and edited this morning, so I had to get up. You're going to see the world premiere of the Hershey Kiss experiment. When you toss a Hershey's Kiss, it sometimes lands flat and sometimes lands on its side. What proportion of tosses will land flat? So that would be what I called in the video landing on its base. The point estimate for that is 0.22. And I'm going to cite the video on that. The population is all Hershey's Kisses. Like all that were ever made in the history of Hershey's Kisses. But the sample we took, or I took, was 50. I actually had to take some out of that bag. If you're interested in buying some Hershey's Kisses, they come about maybe 70 in a bag. So I tried not to pig out last night on Hershey's Kisses to make it work. The parameter is when we just write regular, the regular letter P, and that's going to be the true proportion that land flat or land on their base. So it's really easy with a coin, right? Coin's 50-50. There's two sides. It's equal. But there's no real clear indication just by looking at a Hershey's Kiss how many times it will land on its side versus its base. So my estimate is 0.22, but who's saying that that's the actual number? So P is standing for whatever that actual number is out there. Like if you did this 1,000,000 times, what proportion is it getting closer and closer to? That would be the law of large numbers. Okay, in the statistic, now I put a little hat on the P. And the little hat says this came from a sample. And that's this 0.22 number. So I did 50, I got 0.22, but I'm still wondering, what's the true number that's out there? Was this too small? Was it too large? Right? That's the question. Was the sample a random sample? Yes, it was, because they were not special kisses. They were just regular Hershey's Kisses. You know how you can get those big honkin' ones around holiday time? The big kisses that are about the size of your fist? You ever seen one of those?
No.
You've never seen one of those? It's like a gift you would give somebody. You know, here's a big giant kiss. I would wonder if you would get different proportions from big kisses than from little kisses. I don't know. What is the formula for calculating the standard deviation of the sampling distribution of p hat? Well, that's a mouthful, but it's appeared in many of our videos. The standard deviation of p hat is the square root of p, 1 minus p over n, the sample size. What condition must be met to use this formula, and has it been met? That's the 10% condition. And what that means is I didn't sample more than 10% of all the kisses that are out there in the world. So 50 is less than 1/10 of all kisses. We don't know the value of P, and that's the whole point of a confidence interval. So we'll use P hat instead and calculate the standard deviation. So you notice that formula says P, like the actual P, if we knew it, but we don't. So instead, we're going to roll with what we've got. And this now is called the standard error. When you do this, when you make this little substitution of P hat, 1 minus P hat over n. Again, that's why they call the class statistics, because we're using something from a sample. Whoops, this is 0.22. And that would be 0.78 over 50. I got to calculate that answer because I didn't know what I'd get this morning. Okay, it looks like it is, I'm going to go 3 decimals here, 059. And number 7, would it be appropriate to use a normal distribution to model the sampling distribution of p hat? And what you got to do to justify normality is, we call this large counts. Did you have at least 10 successes and 10 failures? Yes, I had 39, we would call those failures. Those poor little kisses on their side. And 11 successes. So that means this will work. Let me write that down. each greater than or equal to 10. Okay, do you have any questions so far? All right, number 8. In a normal distribution, 95% of the data lies within how many standard deviations of the mean? Okay, so this is the 68, 95, 99.7 rule. So 95% of the data lies within 2 standard deviations of the mean. Calculate the, and now here's a new term, margin of error for a 95% interval by multiplying the critical value. Now, this critical value is actually what the 2 is. And standard deviation you found. So it would just be 2 times 0.059. Which is 0.118. So I know you guys have heard margin of error before, especially when we're talking about surveys and polls, but you know, between politicians. That's how you calculate a margin of error. You take some critical value, and they usually don't tell you this on the news, but it's either 90 or 95%, and then times the standard deviation. All right, now with that number, we can actually find the point estimate, the confidence interval using the point estimate. So point estimate is 0.22. That means what did you get from the experiment plus or minus the margin of error, which is a critical value. Critical value just means how many standard deviations out do you want to go times the standard error. Okay, so it's going to give us a low endpoint and a high endpoint. So if I do the subtraction, I get 0.102, or about 10.2%. And now if I add it, 0.338. Okay, so even though I got 22% by dumping out the kisses one time, the statistics say that somewhere in there is probably the true value. How confident? I'm 95% confident that it's in there. Now, number 11 doesn't apply anymore to us because we would be doing this in class, and I would have I would have given out probably 5 kisses to each group, each pair, and then you would have done it 10 times, and then you would tell me what happened. But basically, what I would have expected is that if this was a number line, and you guys then reported to me what your particular confidence interval would be, because they're all probably going to be different. There would be some over here, some over here, you know, but 95% of them would be capturing the true value. Now, I'm going to tell you what I think the true value is based on what I've heard from other statistics teachers. And it is 35%. So my confidence interval failed this morning. I don't know if it's because I dropped them from about 4 feet up. I don't know if that has something to do with it, or, you know, just simple dumb luck or whatever. But the point is that if we did this as a class, 95% of us would have had successful confidence intervals that captured that true value. So really number 12, what do you think? Well, I just told you. It's probably about 35%. Do you have any questions? We're on the notes part. 3 important ideas. All about the same width. Okay, so remember, conditions are important because they give us reasons for being able to do what we did. There were 3 things that were conditions. The first one was it had to be random. In other words, you can't go picking through a big bag of Hershey's Kisses and trying to find ones that are abnormally shaped. Or you can't be, for example, eating the little tip off the end and then rewrapping it because now you've just changed it, right? The second thing was the 10% condition. Means I can use standard deviation formula. Because remember, to truly be a binary experiment, I would have to basically toss one Hershey's Kiss, put it back into the population of all Hershey's Kisses, and then randomly pull out another Hershey's Kiss. So that's silly, right? As long as we don't get more than 10%, we can go ahead and use this standard deviation formula. And condition number 3 is large counts. Large counts means 10 successes, 10 failures. And this is, the purpose is, we can assume normality. And that means we can use the Z-chart. Or in this case, we use the 68, 95, 99.7 condition. Now, the next part, critical values. Now, 95%, the critical value is 2. In other words, if you want to capture 95% of the data, you have to be within 2 standard deviations of the mean. Well, the question would be, well, what if I don't want 95%? What if I want a different percent? So let me show you that right now. Sort of off to the side, I'm going to do a geometric diagram for you. Okay, so let's say this is our normal curve. And let's say that I want to be 90% confident. So in other words, 90% of the data is here. Now remember, the normal curve is symmetric. The left side looks exactly the same as the right side, even though I rarely draw it that way. So how much data would be here or here, where I have the question marks? Well, it has to all add up to 100%, right? So if it's 90% in the middle, then the 2 areas to the side have to be 10%, and that means that each one has to be 5%. Well, What I really am after, though, is what is the X location where I get 5%? Well, good news. That comes from the Z chart. So let me pull up a Z chart. And I'm going to show you in there. Yeah, I got to change my screen. Okay, here's a Z chart. I'm zooming, but it doesn't get any bigger on my screen. So you guys are going to have to pinch open on your screens. What I'm looking for is inside of the table, I'm looking for something close to 5%. Now, I may not get it exactly, but I'm looking for some number inside of here, 0.05. And it's really close right here. Can you see where I'm circling with my mouse?
No.
That's
Yeah.
okay, there's my mouse. It's here. One is at negative 1.64. And the one right next to it is negative 1.65. If you are that many standard deviations away from the mean, then you're capturing 90% of the data within that many standard deviations. So those who have studied this a little bit more in detail, on the left side it's negative, well, let me change with my screen here. There, it's negative 1.645, but on the right side, it's positive 1.645. So what we end up doing is we just take the absolute value of this and we say 1.645. That's the magic number that gives you 90% of the data, or 90% confidence. Now, what if I wanted to be even more confident? Let's do the number that is for the homework or for the assignment. For the assignment, you're going to need 98%. So I'm going to go through and erase some of these. It would be 1%, right? Because it's 2% divided in half. So then when I go to my Z chart, I'm going to look up something really close to 1%. So I'm looking in the table, I'm looking for 0.01. 0.01 is really close right there. It's negative 2.33. No, I can get even better than you can get. It's a negative 2.33. With a graphing calculator, you can get an even more accurate number for that, I'm sure. But we'll go with negative 2.33. Okay, so negative 2.33 is what you're reading from the Z chart, but I just need the positive value. So 2.33 is the critical value for a 98% confidence. In other words, if I was at 95%, I would go 2 standard deviations out. But because I want to be a little more confident, I have to widen out my interval. And this is the number, the magic number, that makes it so that you can capture 98% of the data. Think about it this way. it's like having a net. Okay, here I am hunting butterflies with my net. Can I do a picture of a butterfly? There. Okay, wait for it. You're going to love it. There it is. This is my butterfly. Okay, well, let's say I'm not very good at butterflies. How can I be more confident that I can capture a butterfly? Well, get a bigger net, right? Get a bigger net, you can catch more butterflies. And that's what the relationship is here between these things. Okay, so let's go back over here to the notes part. To find any percent you want, look up.
Mr. Stewart,
Yes.
what part of the distribution does the negative number represent?
It's the left side.
So like if it, like for 95, it's positive 2, so it's the middle part?
No, what we're saying is, you know how we did a plus or minus on the earlier problem? Well, that plus or minus takes care of the fact that it could be negative or it could be positive. Do you want me to scroll back and show you exactly what I'm talking about?
Yeah.
Okay. Okay, wait for it on your screen. I think Zoom is really slow today because lots of people are Zooming. Okay, I think it's on your screen. Do you see the plus or minus?
Yeah.
Both critical values. That's why you don't have to really care about plus or minus because it's going to come out in the formula anyway.
Okay.
That's, I mean, in the Z chart, instead of looking up, say, 1%, I could also look up 99%. And it's going to give me just the positive number, 2.33.
Mm-hmm.
So it doesn't matter which side you get it from of the normal curve, left side or the right side.
Okay.
Okay, so if you want to find any percentage, look up. Okay, so you have to do 100% minus X will be the thing you want and divided by 2. But that, remember, you have to look on the margin or the margins because you got to get one from the left and one from the top. Okay, number 3. So this is number 1, number 2, number 3. Confidence interval. So it's a point estimate. And a point estimate just simply means what did you get from your experiment? Plus or minus a margin of error. Now, how did you get your margin of error? Well, margin of error comes from the critical value. You know what I forgot to do? Under critical values, I forgot to tell you the variable that's used for that. And it's called, this is a good reason why I like to put a slash through my Z's. It's called Z with a star. This is the critical value. So it's your, in symbolic language, it's your p hat, which is your proportion coming from the experiment, plus or minus Z star, which is your critical value. It tells you how many standard deviations you want, times the square root of, now this would be standard error, so it's p hat 1 minus p hat over n. I know it looks complicated, but remember, if you just go through the lesson, how did we build our confidence interval? That is how we built it, a little piece at a time. Man, there's a funny graphics on that. There we go. Looks a little better. Okay, any questions? That's about an hour right there. Say that one more time.
What does the Z star mean?
The Z star stands for the critical value. It means how many standard deviations do you need to go out to capture the percentage you want. So for example, if let's say your Z star was 1, then how much data would you be capturing? Okay, I guess I was waiting for an answer there. You would be capturing 68%. Because remember, the 68, 95, 99.7 rule, right? It says if you go 1 standard deviation out on either side, you've captured 68%. If you go 2 standard deviations out, you get 95%. If you go 3 standard deviations out, you've captured 99.7%. So there has to be numbers for all of those in-between percentages, right? I mean, say you wanted to have a weird percentage, like 93% confident. Well, there's got to be some number out there that will do that for you. And it's sort of a reverse lookup on the Z chart, right? That we began the year by using the outside to get the inside number. And now we're using the inside numbers to get the outside number. So let's go down into the check your understanding question about sleep awareness, and just make that real clear here. So this 98% in the problem, that means that the Z star, that's why we looked it up together, is 2.33. So you're going to have a point estimate plus or minus this 2.33 number times the standard error. That's how you're going to put your interval together. Your point estimate is going to come from the experiment or the survey. Your standard error is going to run through that formula for standard deviation. And the 2.33 just says this is how many standard errors you need to go to get 98% confidence. So please think of confidence intervals as giant nets. You want to capture more things, you got to use a bigger net. It doesn't make your aim better, right? Really, your aim is determined by the size of the sample. The confidence is, I mean, you can have a really bad fisherman, but because he's got a gigantic net, he can capture fish, right? Different than maybe an expert fisherman who could just take a sharp stick and aim it directly at a fish and he's got it.